Right, here we go. Number 3, cosine to the fourth power of x plus cosine squared of x equals 2, and we are going to solve that on the intervals from 0 to 2 pi. The first thing I want to do, I have powers here in my trig function, so I'm thinking, okay, I probably have to factor something out here, so I want that equal to 0, so I'm going to move that 2 across the equal sign first, so subtract 2 from both sides. So I have cosine to the fourth power of x plus cosine squared of x minus 2 equals 0. And then I'm looking at that and I say, well, okay, that's kind of an easy one to factor, right? Hopefully you see that too. And if you don't, you probably should review a few little factoring. That would just be a cosine squared x and a cosine squared x. And then what's going to multiply to give me a negative 2? That would be a negative 1 and a positive 2. Why do I want a positive 2? Because my middle term here is going to be a plus right there. So I need a positive. So plus 2 minus 1. Okay. And then I have now the zero product property, right? I multiply two factors that are equal to 0. So we're going to split them and say, okay, cosine squared of x plus 2 equals 0. Or cosine squared of x minus 1 equals 0. So cosine squared of x plus 2 equals 0. Subtract 2 from both sides, and you're going to have cosine squared of x is equal to negative 2. And at that point, I can already stop, right? I am going to take a square root on both sides. This is going to end up being an imaginary number. So right here, I just want to be in real number for solutions for now. So we're going to say no real solutions for that one. And we're going to move on. And then on this one, cosine squared x minus 1, you're going to add 1 to both sides. We are going to have a cosine squared is equal to a positive 1. Take a square root on both sides. And that will give us a cosine of x equals, now we take a square root from something here, so it will be plus or minus 1. And the cosine is going to be positive or negative 1 at 0 and at pi. So the solution here will be x equals 0 and x equals pi. We probably... No, I think we're good. I don't think we need to check the solution. I mean, you can always check the solutions, right? You can always say, I want to check my solution. You're going to plug that into your original equation. So we would have the cosine to the fourth power of 0 plus a cosine squared of 0, and we want to know, is that equal to 2, right? When you're checking, you put a question mark on the equal, right? Because you don't know if those two are equal. You're checking if it's true. And then cosine of 0 is 0, therefore 0 to the fourth power is going to be 0 as well. Cosine of 0 is 0, therefore 0 squared is going to be 0 as well. I hope you laughed at me here from afar. Cosine of 0 is not 0. I'm not sure what I'm babbling about. Cosine of 0 is 1. Yeah, did you have a good laugh? And then 1 plus 1 equals 2. There we go. Sorry about that, guys. And then you will do the same with pi, right? Cosine of pi will be negative 1, but then the negative in an even power will give you a positive 1. And then cosine squared of pi, the cosine of pi is negative 1, but negative 1 squared will be 1 as well. Therefore, that will work as well. And so both of those work. All right, moving on to a next example. Example 4, I think, is where we are. Yes. So we're going to do a double angle here. Sine of 2 theta times cosecant theta equals 1. Okay, so you're looking at that, and there is no square. There is nothing that you could use the Pythagorean identities So, but you do see an identity. I hope you do see it. This is a double angle for sine, so I can rewrite that as 2 sine theta cosine theta, and then keep writing what you already had, which was the cosecant. Oh, well, how about that? How about we just go ahead and change that cosecant so that we only have sine and cosine, and the cosecant theta will be the same thing as 1 over a sine theta. Okay, and now that I have that, I can see that those two will cancel, right? That will just be a 1. So we have a 2 cosine theta equals 1. I'm going to isolate my trig function, so it will be a 1/2. And from the unit circle, we know that the cosine is equal to 1/2 when we're up here and there, right? Positive 1/2, so it will be in quadrant 1 and in quadrant 4. And so therefore theta is equal to pi over 3 and 5 pi over 3. Now that will be for my general solutions. And then if I wanted my sorry, those are the particular solutions. And then if I want the general solution, we're going to have to remember that the period of cosine, because that's what I have at the end here, cosine theta, right? The period of cosine is 2 pi. And so theta will be equal to pi over 3 plus 2 pi k, and theta is equal to 5 pi over 3 plus 2 pi k, and we're going to say that k is an element of the set of all the integers, okay? And by now you should be all comfortable doing those general solutions. Okay, we're going to go on to example number 5. And for this one, I picked something that's a little bit more complex, and it involved a lot of all the different things we've been doing, right? Different identities. So 4 sine of theta plus 4, that's a plus, sine of 3 theta equals 0. Okay, so I have a sine with a single angle theta, and I have a sine where the angle will be 3 theta here. So I need to do something to split that up. So I'm going to rewrite this sine 3 theta using sine 2 theta plus theta. Okay? And that's because I have an identity for a 2 theta, and I have an identity for a sum of 2 angles in a sine. So all of that is going to be good, right? So, okay, we have 4 sine theta. What we cannot forget is this 4 right here, right? We cannot forget that 4, and I'm going to open a bracket because I'm going to split that. Now I'm going to write that using the identity for sums of angles in sine. And so that will be the sine of the first angle, 2 theta, times the cosine of the second angle, which will be theta, plus the cosine of the first angle, which will be 2 theta, times the sine of the second angle, which will be theta. Okay, so that's using the sum identity for sines. And now I have to look and see that now there are several ways you could be doing that. And in fact, I tried several ways, and some get more messier than others. So you really have to look, but I have now a sine 2 theta here, and I know sine 2 theta will be 2 sine theta cosine theta, and I have a cosine 2 theta here, and that could be 3 things, right? That could be different things. And that's where I tried several things, and really I don't think one works better than the other. So I'm just, since I have a sign here, I'm just going to go with the one that's the 1 minus 2 sine squared theta, just because I have that sign there. Okay, so now what else did I not use it? So I need to finish writing everything down here. 4 sine theta plus, we still have that 4, and then 2 sine theta cosine theta times that cosine theta, right? Plus that cosine 2 theta became 1 minus 2 sine squared theta times sine theta equals 0. All right, if you're not convinced, make sure you're walking your way through and try again, right? Make sure you're following along with me here. Okay, so now what else can we do? Well, I'm looking and I'm noticing that I have a cosine times a cosine here. That would be a cosine squared theta. But I have a sine here, so I'm thinking, I don't know, maybe I want a sine as well here. So cosine squared theta would be the same thing as 1 minus sine squared theta. So here we go. Navy blue is good. All right, so we have 4 sine theta plus, and now I'm going to multiply. So we have that 4 times that 2 times that sine. That'll be 8 sine theta times this, right? Plus, and I think I'm going to go ahead and already distribute this one since we're good to go, but I can't forget, this was also multiplied by 4, right? That 4 multiplies everything in the bracket from here to here. So all of that is multiplied by 1/4. So I'm going to have 4 times 1 times sine, so that's 4 sine theta, minus 4 times 2, which is 8, times sine squared sine, that's sine cubed. Okay, if you're not convinced, make sure you're pausing the video and think through that again, right? Okay, so now I still want to multiply this here, so let's do that. And then at the same time, can I go ahead and put those like terms together? 4 sine theta, so it'll be 8 sine theta plus, so that will be 8 sine theta, and then 8 sine multiplied by a negative sine square will be negative 8 sine cubed theta. So this 4 here was already combined with this one in my 8 sine theta here, so now I still have that minus 8 sine cubed theta. Okay, and when you're looking, we have like terms here and we have like terms here, so put those together will give me 16 sine theta minus 16 sine cubed theta equals 0. And I can't solve anything here, right? The zero product property, it's in the name, zero product property. Only works when you have a product, right? So I need a product to be able to split it. And so I'm going to factor to create a product. So I have a 16 sine in both of those terms. So I'm factoring out 16 sine theta. Well, what is 16 sine theta divided by 16 sine theta? Well, that's just a 1. Minus, and then 16 divided by 16 is 1. Sine cubed divided by sine is sine squared, so that will be a sine squared theta. And at this time, you could rewrite that as a cosine square, but I'm ready to split this in two. So I have multiplied two things, the 16 sine square, the 16 sine theta, and the 1 minus sine square theta, and it gives me a 0. So I can split that, say 16 sine theta equals 0, and 1 minus sine squared theta equals 0. All right, divide by 16 on both sides is not making a difference because you have a 0, so it's still 0. And we know that sine is 0 at 0 and at pi. So theta would be equal to 0 and 2 pi. And then this one, we're going to finish it up by taking now a square root. So don't forget your plus or minus here, or you're going to miss some solutions. And we're going to know that the sign is going to be positive 1 up here and negative 1 down here. Therefore, theta has to be equal to pi over 2 and 3 pi over 2. Now look where all those solutions are. Right there, right there, right there, right there. So all my solutions are going to be pi over 2 away from each other. And when I want to write my general solution for that, I'm going to use that fact and kind of, I don't need as many, right? So the period of sine is 2 pi. So the general solution, but we have symmetry, right? We have symmetry for the solution. So we want to think, attention, we will use the symmetry of the solutions. And so I'm going to say theta, oh, that's bad, theta is equal to pi k, and theta is equal to pi over 2 plus pi k. And when you think about it, so is my 0 included in that? Well, yeah, if k is 0, theta is 0. If k is 1, theta is pi, 0, pi. If k is 2, theta is 2 pi. So we're back there again, right? And do the same here, and you should see that all of that would include all of your solutions. All right, I have, I think, 2 more examples I wanted to do, so let's see. Example 6. We're going to do a tangent, a double angle tangent, because we don't want to forget about those tangents. And this one is kind of an interesting problem, I thought. Okay, here's what we have. And the first thing I want to notice is that I have 2 terms and they both have a tangent to theta. So I'm going to factor that out first. Which means that's going to become a 1 minus, and then this will just be tangent squared theta equals 2. Now it's not equal to 0, so we can split, right? Don't you split anything. We cannot do a 0 product property unless we have a 0 here, so we can't do that. But what can I do is, I have a double angle, and we know we don't want to keep that double angle, so I'm going to rewrite that using the double angle for tangent, and we need to know those. Did I ever mention you have to memorize those identities? Wonder. 2 tangent theta over 1 minus tangent square theta. So that will be just the double angle for tangent, and that's multiplied by still that 1 minus tangent square theta equals 2. When you're looking at that, can you see how, oh, nice, right? That's just a 1. So all I'm left with is 2 tangent theta equals 2. And then divide by 2 on both sides. Tangent theta equals to 1. And where is the tangent equal to 1? Well, tangent is positive 1 in quadrant 1 and in quadrant 4, 4 pi over 4 and 5 pi over 4, right? So theta is equal to pi over 4 and 5 pi over 4. And then for the general solution, we're going to remember that the period of tangent is pi, and so we're going to have general solution of theta is equal to pi over 4 plus pi k, where k is an element of the integer. And I'm going to let you think about, well, how about this one, Mrs. Williams? Did you include that? Well, you think about it and you see if it's included in that general solution, okay? All right, I need to hurry. We have one more example to do, and the janitors are almost going to come in the room here, so let's hurry up. Sine 3x plus pi is equal to negative root 2 over 2. Now this one is kind of a different one, and I thought that was important for us to look at an angle that's written like that. I need you to think about that like this will be sine of beta, right? Think about 3x plus pi to be just a big old angle, and so we have a sine of some kind of angle that's equal to negative root 2 over 2. So you want to ask yourself, what kind of angle gives me a negative root 2 over 2, a sine? Okay, well, the sine is going to be negative in quadrant 3 and 4, and the negative root 2 over 2, those are the 45s, right? The over 4s. So that will be when that angle beta, which is really not beta, so I'm going to stop calling it beta, and now I'm going to give it what it was again, right? So 3x plus pi, that big old angle, is going to be equal to either 5 pi over 4 or 3x plus pi is going to be equal to 7 pi over 4 in quadrant 4. Yes, quadrant 4. Okay. So now I want to isolate my x, right? So I'm going to subtract pi from both sides. That becomes a negative 4 pi over 4, so that'll be a pi over 4. Now I need to divide by 3. Okay, so that's my first one. And then do the same here. You're going to subtract pi, so that becomes a negative 4 pi over 4 for a common denominator. So that becomes 3 pi over 4. And then divide by 3. That's just going to cancel that 3 in the numerators, right? X equals pi over 4. Okay, two solutions. But my angle is complex here. And so I'm wondering, are those the only solutions on 0 to 2 pi? And we already know with dividing by pi over 12, we know there is going to be more than that, right? Okay, so those are two of the particular solutions, but there might be more particular solutions. Okay, so let's find the general solution, and then let's use those to find all the other particular ones. So general solutions. We'll remember that the sine has a period of 2 pi. Oops, can't spell anymore. And so we're going to, and at this point, I need to go back all the way here and all the way here. In fact, I could do that, and I could use that, right? I really could, but let's go all the way here. So what we had to start with in our trig function, 3x plus pi, and we said that was equal to 5 pi over 4, and the other one was 3x plus pi. Come on. Trying to hurry, and now I mess up. 3x plus pi is equal to 7 pi over 4. And we want the general solution, so we're going to say period of 2 pi, so we're going to say plus 2 pi k plus 2 pi k, where k is an element of the set of all the integers. All right, so we're going to simplify that. So we're going to subtract pi. So the like term of pi would still be my 5 pi over 4. This is why I said we could have used that right there already, right? So 3x equals, subtract that pi, will give you that pi over 4 plus the 2 pi k. And now we need to divide by 3. And this is why it was important that we went back to either this one or this one where we have the 3 with the x, right? Because now when I divide by 3, I need to divide every single term by 3. So I need to divide by 3 here, by 3 here, and by 3 here. Okay, that's important or you wouldn't get the right answer. So that would give me x equals, and that was pi over 12, still going to be pi over 12, and that will be plus 2 pi over 3k. Okay, and now we do the same with this one. So we're going to have 3x equals, and we add pi to both sides, will give me my 3 pi over 4 back plus 2 pi k. And then I'm going to divide by 3 everywhere, right? So x equals, divide by 3, that's 3 cancels again, right? Like we did earlier. Plus, and then divide by 3 will be 2 pi over 3 and then k. That will be the other general solution. So now we're going to use those two to find all particular solutions on the interval 0 to 2 pi. Okay, so we're going to have x equals, our very first one was pi over 12. Our very next one was pi over 4. Okay, so pi over 12 here is when k is 0. Pi over 4 here is where k is 0. So let's put a k equal 1 here and see what we get. And put a k equal 1 here and see what we get. Put a k equal 2 here, see what you get. K equal 2 here, see what you get. And you keep going until you're going to have something that's smaller than 2 pi, right? Something that's smaller than 2 pi. So, and I already did them, so I'm going to just list them, but you guys need to make sure you're finding your way through to solve those. And again, right, this is just a matter of plugging in integers for k here. And you keep going, keep plugging integers for k until you reach something smaller than 2 pi. Until you reach something equal to or bigger than 2 pi. That's when you know that was too much, you need to stop. And those are your particular solutions between 0 and 2 pi. All right, we're going to call it a night. Good night.